Welcome to BKW Physics. I'm Mr. McConley, and today we're going to talk about fission. Fission. And fission is when you take a large nucleus and you break it into smaller nuclei. Now, remember, if you back up, there was natural decay and there was induced. Now, fission is something that is induced. We are wanting this to happen, and the reason we're wanting it to happen is because the product will be a huge amount of energy. That's why we're wanting it to happen, because that energy we have uses for it. And I'll get to that in a moment. But let me spell out a typical fission reaction. If you have 235-92, which is uranium, by itself it will decay, but if you induce it with a neutron, now you're really going to speed up this process, and what it's going to decay into is a 92-36 Kr plus a 141-56 Ba plus you're going to get 3 more neutrons. Now you can check my math here to see that I got this right. On the top you got 235 plus 1, 236. 92, 141, and 3 gives you 236. And on the bottom it's got to add up to 92. It adds up to 92. Alright, so at a glance you're thinking this is all balanced, and in chemistry we'd be happy, we'd move on, it's a balanced equation.Hu, what we've learned previously in physics is that because when you carry these out, it's 1.0087, and when you break them into the constituents, the neutrons and the protons, and then you start adding it up, this is not quite equal, not quite balanced anymore. And the name for it is there is a mass defect. This should be a review at this point. And if you go back to that lesson, you can see the details of how mass defect plays out. But basically, this side, when added up, does not add up to this side. In fact, in this equation, the left-hand side actually has more mass, and this side over here actually has less mass. Now, the example I gave was in my previous lesson was with mass defect was something small. I think it was a nitrogen. And so the differences were also small. But now we're talking about uranium, where you have 235, much, much larger. So you're exponentially expanding the mass defect. This number has become much, much larger. Now the way that this balances out, because things have to balance out, the way that it actually balances out, this is short on mass on this side, so we're going to have to add something on this side. But you don't add mass out of the blue sky. What you get is you get a whole bunch of Q. And what did Q mean in chemistry? Energy. You guys are quiet, but I heard a couple people whisper it. So when you get a big Q on the end, you get energy. And what did Einstein say about energy and mass? They're not exactly equal, but they're equivalent. Like if you got one, you got the other. So since we're getting a bunch of Q, a bunch of energy here, that's going to kind of help balance our equation. So now this side will equal this side. This is the part we're really, really interested in a fission reaction, because we can use this. How do we use this? Well, since you got a lot of energy, and the energy usually comes in the form of heat, the heat can be used to heat up water. And when you heat up water and it changes phase into steam, the steam can be used to turn a turbine. And if you can turn a turbine, you can make electricity. Alright, so you're heating water, you're making steam, you turn the turbine spinning with magnets and coils of wire and magnets. And when that happens, boom, you can make electricity. And so the only reason you're doing the fission reaction is to create the heat energy. That's all you really want here. You really don't want these things because these are radioactive materials that you have to get rid of, and then you got waste. So this stuff here is waste. This is what you want right there. Alright, so there's the process. Now, once you get this and you can turn a turbine and make electricity, what do you do with that? Well, you can have a nuclear power plant. You could have a nuclear submarine. You could have a nuclear-powered aircraft carrier. And the cool thing about these two right here, the uses for the military, is that once they get this fission reaction going, they only really have to fuel it up every 20 years or so. Okay, so if you had a normal ship, every time you come back to port, you'd have to put fuel in it. You'd have to, you'd always be fueling the thing up. But with nuclear power, this thing's good to go for a long time, 20 years. So they can use that power effectively. You still do get the waste, but not as much. Where a nuclear power plant, since you're trying to generate power for the whole grid in the United States, we'll say, you're going to need to keep adding more fuel constantly. And the fuel is, of course, the uranium. Alright, so let's go through some of the things that you'll find in a nuclear power plant, or a nuclear sub, or an aircraft carrier. These are things that appear whenever you have a fission reaction. First of all, you got to have the fuel, the nuclear fuel. And some popular nuclear fuels are the one I've shown, uranium-235. Another one is plutonium-239. These work well. You got to have a very large nucleus. Now, usually these are made into long rod-shaped objects. So they take the uranium, they make it into a rod, and then the rod can be inserted down into the reactor or pulled out. That's just the way they tend to do it. The next thing you got is moderators. Just like a moderator in a argument, the moderator is meant to kind of smooth things out and keep it moving at the correct pace, the conversation, or in this case, the reaction. So a moderator is something like water, graphite, heavy water. What it is it's going to kind of take the edge off. This is a very hot reaction, and you got to kind of take the edge off. The moderator, the pool of water that the reaction sits in, that's what we're talking about. The next thing you got is a control rod. Now, a control rod has a really important job. The control rod needs to absorb neutrons. If it fails to do that quick enough, this reaction gets out of control. Let's go back to the reaction again for a second. A few things I haven't mentioned about the reaction. The first thing I haven't mentioned is that this is a chain reaction. Okay, I didn't say that yet, but this is a chain reaction. What does that mean? Well, how did we get it started? What's the words again? We induced it with a neutron. Now, after this happens, what did we end up with? Neutrons. How many? So think of it this way. You start it with one neutron. The reaction starts to happen. You get 3. Those 3 are still parked next to the uranium, because remember, I'm drawing this on the board, but you got to think of a chunk of uranium or a rod of uranium, and then this reaction's taking place, and so right around this rod of uranium, you get 3 more neutrons. What are they going to do? They're going to induce 3 more times this, and 3 more times is going to give you, and the thing goes, it gets really big really fast. And that's where you get so much energy from, but it's also where you get so much lack of control if you don't have the control rods working perfectly, because the control rods need to absorb neutrons. If they don't absorb enough, then this chain reaction, because it's a chain reaction, because once it starts, it just keeps going, it keeps perpetuating itself. So if you don't absorb enough neutrons, it'll get bigger and bigger and bigger, and there's a point you don't want it to get bigger, because you don't want it to melt through the container, so you have to absorb neutrons. It's a chain reaction. Okay? One other word that shows up a lot is critical mass. It's a word that most people don't know what it means, but what they're referring to there, it's the minimum amount of fissionable material that you need to keep the chain reaction going. So there's a point where you get so low on uranium that the reaction won't happen anymore. Okay, there's not enough uranium for the neutrons to react with, and the thing kind of peters out. But critical mass is when you have the minimum amount of fissionable material still available for the chain reaction to keep going. Okay, in critical mass, I've heard it like used in movies. It's like, ooh, scary critical mass, but that's all it means. You just have the minimum amount to keep the reaction going. Now, in terms of back to what you find with a nuclear reaction, you'll also find coolants. And coolants are, again, things like H2O, water, but they also use molten Na, because it just tends to be able to absorb the heat well. And this is actually in the Chernobyl incident in Russia, where the reactor actually melted down. A lot of things went wrong, but ultimately the coolant wasn't cooling enough. Okay? Now that probably was backed up because the control rods didn't absorb enough, and et cetera, but there are a lot of issues, but ultimately, when you can't cool the thing down enough and it becomes hotter than the container can handle, you're going to melt through things. Now, to protect people working near this, or if like you're in a ship and you're living in the ship, you got to be protected from this reaction, so you need shielding. And I before E except after C. Spelled that wrong. But shielding. Now, steel can be used for shielding. Concrete's even better. But I'm sure you can imagine that on a ship, you don't want to be putting a lot of concrete to shield you, because you're adding a lot of mass there, so that's not really a great idea. But if you're doing this on a power plant, the shielding with concrete is great, yeah?
Do they ever use lead for shielding in power
Yes.
plants?
Yes, lead is another really good one. But again, the mass of it is restrictive. So you got different types of shielding. The other thing you're going to have, ultimately, is a lot of radioactive waste. And this is where much of the controversy using nuclear power comes from, because we do not have a good way to store or keep this radioactive waste away from people once we've created it. We don't know what to do with it. We don't have a great solution to handle it. Now, there's different types. There's solid and liquid radioactive waste. There's what we call low-level waste, which can actually be discharged into a water body because it's not enough to bother anything. We have gaseous radioactive waste that can be let up into the sky. And again, it's not at a level that's going to harm anybody. But the solids and the liquids are the ones that are hard to deal with, because you're not talking like, oh, we'll wait till next week and it'll be safe. It's millions of years. So you have to figure out a containment system that is going to sustain millions of years, and that's hard to do. So I hope this quick synopsis of fission makes it a little clearer for you. For today, physics.